Alright, welcome. In this video, I'm going to be working through volume calculus problems that require the disk method. Okay, I'm going to be going through my extra practice worksheet, and I might also do the practice problems that I have on my online practice in this video as well. So let's get started and look at this one. Okay, region R is bounded by the graphs of 1 plus x cosine x and y equals 1. Find the volume of the solid formed by rotating R around y equals 1. Okay, so it's going to be disks because we're rotating it around the line that the region is entirely touching. So I'm going to go over here and I'm just going to set up. So for number 1, I've got something that kind of looks like that. And then that's also my axis of rotation. Okay. I'm going to need a radius because I know that for disks, volume equals the integral of pi r squared dx or dy. Okay, so I need to draw my little representative rectangle so that I can figure out what the radius is. Okay, this is going to be my radius when I rotate around this horizontal line y equals 1. And so I need to write down r in terms of x. Okay. So r is equal to top minus bottom. Okay. On top we have the curve, 1 plus x cosine x. And on bottom we have y equals 1. Okay. So 1 plus x cosine x minus 1 is just going to be x cosine x. Okay. And then, yep, so I've got what I need. I know my volume formula is volume equals pi times the integral from this is x equals 0 up to some x value I'm not sure about yet, but I know this is going to require a calculator, so, you know, eventually I'm going to take that r and I'm going to square it and integrate with respect to x. So, you know, I'm going to have to use a calculator eventually, so I might as well use it to figure out, oh, no, wait a second. I don't need a calculator for this. Real quickly talk about x cosine x. So I'm interested in where those two curves ran into each other. So that would be y equals 1 plus x cosine x was equal to y equals 1. Right? The curve ran into the line. And so that's where I subtract, and I get x times cosine x is equal to 0. And we know that if we have two things multiplied together equaling 0, that one of them's got to be 0. Either x is equal to 0 or cosine x needs to equal 0. And x equals 0, well, that's the first intersection right there. Okay, the second one is going to be the first time where cosine x equals 0. Just to remind you, on the unit circle, x represents the x coordinates, so that would be the first time cosine x equals 0 at x equaling pi over 2. So now I know that this is pi over 2. Okay, so what I'm going to type into my calculator is volume equals pi times the integral from 0 to pi over 2 of r is x cosine x squared dx. Okay, and all of these problems that I'm going to do, I'm just going to set them up, but I'm not going to evaluate the integral in the interest of time, because again, I know y'all know how to type an integral into a calculator, and if it can be done by hand, I'll probably do it by hand, but if it's one like this, it's going to require the use of a calculator anyway. I'm just not going to do that in this video. Okay, number 2, and I feel like I need a better pen than this. Number 2 is find the volume of the solid formed by rotating u around y equals 2, where u is bounded by y equals 2, x equals 0, and y equals x to the 4th plus 1. So I'm going to draw that. Okay, that's much better for me, pen-wise. And so I've got y equals x to the 4 plus 1. And I've got y equals 2 as the axis of rotation. All right. So since this is a disk scenario, I'm going to need to draw in my radius, start at the axis, and reach all the way to the far edge of the region that you're rotating around that axis. Okay, and I'll label our r there. R is going to equal top minus bottom. And it's going to be on top, I've got y equals 2, and on bottom, I've got y equals x to the 4 plus 1. Okay. And, well, that'll just be equal to 1 minus x to the 4, right? Okay. That's going to be my radius. Now, we know that volume is equal to the integral of pi r squared. We can always factor a constant out of an integral. So pi times the integral of r squared as x runs from, it looks like 0 to 1. Yeah. This one, I feel like it's debatable. It could go either way. You know, algebraically, I think it's a little more than what you would typically be asked for from the standard College Board problems. But I think I'll do it anyway. Okay, just to remind you. Okay, if I square 1 minus x to the 4, I'll do that over here, and then it'll just go away. So 1 minus x to the 4 times 1 minus x to the 4, that's going to equal, you know, up here it'd be first, outside and inside, last. Okay. So I'm going to scroll that up once I copy it. 1 minus 2x to the 4 plus x to the 8. Okay. Integrating that, multiplying it by pi. And then I'm just going to take off on that. So pi times x minus 2/5 x to the 5th and 1/9 x to the 9th, x running from 0 to 1. This is rough. But I guess it's not that bad since it's 0 to 1. So it's pi times 1 minus 2/5 plus 1/9. And that'll be a safe place for us to stop. All right. Number 3, find the solid volume of the solid form by rotating u around the y-axis. Okay, so I'm just going to reproduce my sketch of u. And we're going to rotate around the y-axis, which was right here. So that is my axis of rotation. Okay. And if I want to get my radius, I start at the axis and I reach all the way to the far edge of the region I'm rotating. And then that will be my radius. Okay, if I have, this is the line x equals 0, so I'm going to need this as x equals something else, but right now it's written as y equals x to the 4 plus 1. So I'm thinking I'm going to need to go over here and say, well, y minus 1 equals x to the 4. X is going to equal plus or minus the fourth root of y minus 1. But it's plus, right, because x is positive out here. So it's the fourth root of y minus 1. Okay. So my radius, it being right minus left, radius is going to be x equals fourth root of y minus 1 minus x equals 0. So it's just going to be that. Okay, and then I'm going to say that volume equals pi times the integral of r. Well, if I took the fourth root and I squared it, that's just going to leave me with the square root. So, you know, I guess I'm going to need to write it as that 1/2 power anyway, so I'm just going to write it like that. As y runs from, it looks like 1 to 2. Yeah. Okay. And then, well, I can do this. I can anti-differentiate this. I'm going to add 1 to the power, divide by the new power, and then I'm going to multiply by pi also, but I already said that. Okay, pi times 2/3 of 1 to the 3/2 is, well, any power of 1 is 1. So 2/3 of 1 minus 2/3 of, when I plug in y equals 1, well, I'll subtract away and I'll just get 0. And, well, there I go. I've got 2 pi over 3. And that's one we could do by hand for sure. Okay, number 4 is find the volume of the solid formed by rotating v around y equals 1. So v is the one that's like the small piece. Okay. And we're going to rotate around y equals 1. Okay. Start at the axis, reach to the far edge of the region you're rotating, that gives you your radius. Okay. Radius equals top minus bottom. Y equals x to the 4 plus 1. Minus bottom is y equals 1. So that's just going to be x to the 4. Okay. Meaning to me that I'll have volume equaling pi r squared. X to the 4 squared is x to the 8 as x runs from 0 to 1. So this would be pi times 1/9 x to the 9th as x runs from 0 to 1. And that would give me 1/9 minus 0. Okay, I'll be happy with that. All right, number 5 is going to be rotate v around x equals 1. That's x equals 1, and this is region B. So, regardless of if the axis of rotation sits above the region or below the region or to the right of the region or to the left of the region, whatever, you're still going to be using top minus bottom and right minus left to express your radii. Right now there's only one radius, but once you learn about the washer technique, there's going to be multiple radii, and well, still be top minus bottom, still be right minus left. So, r equals, okay, this is x equals 1 minus x equals, we did this already, so I'm going to go back up to here and say x equals the 4th root of y minus 1. Okay. 4th root of y minus 1. And this is the type of one that you could do it by hand if you really had to. It'd just be kind of annoying and a lot of algebra. And I'm just, in the interest of time, not going to be doing that. So, yeah, there's nothing we can do with that. So I'm going to say volume equaling integral from y equals 1 to y equals 2 of r squared is 1 minus the 4th root of y minus 1 dy. Okay, and that's something you could type into the calculator. All right. Now, for the next 3, we're looking at this A, B, and C, and if you worked the equivalent problem set for area and arc length, then, well, probably you're familiar with this diagram. And we've got A, B, and C. Probably nothing with region B. Yeah, I see that, because that's going to require washers no matter which way you rotate it. But, we could build on top of it. That's the cross-section volume, and I'm sure we'll do that when that time comes. So for now, we're going to rotate A around the y-axis. We're going to rotate C around the vertical line x equals E, which is the right side of that, of C. And we're going to rotate C around the x-axis. So that'll be good disk problems. Okay, so 6, 7, and 8. I'll be able to do it on this page. So 6 is A, which looks like this. Okay, that's, I don't know. It's good enough. Around the y-axis, so I like to draw in my axis of rotation for emphasis, and then I'll be going over here. Writing down my radius. Notice it's always the same thing on the right and the same thing on the left. So this is the graph of y equals the square root of x minus 1. Okay, so if I squared both sides, I get y squared equals x minus 1. And maybe I'd add 1, and I get x equals y squared plus 1. Okay, and this is the line x equals 0. So when I go to express my radius in terms of y, it'll be the difference in two x coordinates. Radius is going to equal x equals y squared plus 1, because it's on the right, minus x equals 0 on the left. And then I will, let's say, volume being pi integral from y equals 0 up to, okay, this one, okay, we know the y coordinate of this because the x coordinate of this point is e, and we're on the graph of y equals the square root of x minus 1, so y is going to be the square root of e minus 1. Okay. And okay, we can go from there. R is x squared plus 1, so pi, wait. Oh, where on earth did I get x squared plus 1? I don't even see an x squared plus 1, but x equals y squared plus 1. Oh, okay, I see. It's just so far off, I don't even understand what I was saying. Yeah, y squared. Right, because this needs to be an integral in y. So here, and that's y squared plus 1 squared dy. Pardon me. Major mistake. Okay, number 7. It's going to be rotating C around the vertical line x equals E. Okay, so that's this line here. So I'll need a radius, a representative rectangle. Okay. And I'm going to say, okay, C is got a different curve on the side of it. It's going to be y equals log of x. So that means that x equals e to the y. That's kind of what it means to be a natural log. So I'm going to say, all right, on the right, I've got x equals e. And on the left, I've got x equals e to the y. And then we know that volume is equal to the integral of pi r squared. So integral of pi times, integral of pi times r squared, so e minus e to the squared dy. And we need y to run from, this one goes from y equals 0 up to, okay, this is the curve y equals log of x, and this is x equals e. So the log of e is the exponent I put on e to get e, and well, that's going to be 1. So that's the integral, as y runs from 0 to 1. And then that's something that you could do with a calculator if you needed, but you would not probably be expected to do that by hand. Excuse me. Couldn't get to the pause button in time. All right, so I'm now going to rotate C around the x-axis, and that'll be something we're able to do. All right, so I'm going to need my radius. Okay, my radius will be top minus bottom, y equals log x, minus y equals 0, because it's around the x-axis. And so it's just going to be, radius is log of x, and okay, so volume is pi times the integral of radius squared. Okay, and x is going to run from 1 up to e. Okay. And that one is one that you would have to use a calculator for, because in this class we don't have an antiderivative for the square of log to x, or log x squared, or how you say it. Okay, now the last 4 are going to be, okay, we're going to rotate f around the x-axis, d around y equals 2, d around the y-axis, and e around pi over 2. Okay, so some of these should come out the same, or at least hopefully we're able to see that they're equivalent based on their based on their integrals, but I think these are a bunch of them that I'm not going to be computing because, again, sine squared x and cosine squared x, those are not things that we have an antiderivative for in this class, so I'm just going to use a calculator or just write the integral and walk away. So number 9 is, how far can I go? Yeah, there we go. Number 9 is f around the x-axis. So let's go about like that. This is the x-axis. Give myself a radius. and write it down in terms of x. Okay, well, it's top minus bottom. It's y equals cosine x minus y equals 0, so r equals cosine x. Okay, and then I'll have, volume equals pi times the integral from 0 to the place where cosine x equals 0, right? Because it's where it hits the x-axis. And you need to know where that happens. So we're going to go over here and kind of consult with our unit circle. And we're going to say, where is cosine equal to 0? Okay, it's where x is 0, and it's going to be right here and right there. And that's the first time it's going to happen, on the graph. It's going to be at pi over 2. Of r squared is cosine x squared dx. Okay. And, well, that's an integral that's going to represent what we've got. Okay. Find the solid volume of the solid form by rotating d around y equals 2. Correct. Oh, and hopefully this will... Maybe I don't. Yeah, no, I'd see. This should be the same volume, right? It's going to make half of a football. And, okay, that's D, and looks about like that. And then that's my axis of rotation. That's y equals 2, and this is y equals 2 minus cosine x. Okay. To get my radius, I start at the axis of rotation. I reach down all the way, and I'll get r equals top minus bottom. And you're like, oh, okay. Radius is just cosine x. Okay, and that's going to mean same radius, same volume. Pi times the integral from 0 to pi over 2 of r squared is cosine x squared dx. Now we're going to rotate d around the y-axis, and that's going to be a little exciting because, right, how are we going to solve for it? Just carefully. So d looks like this now. Whoops. All right, and volume of the solid. Okay, I don't know what my problem was here. This is y equals 2 minus cosine x. Okay, if I need to solve for x in terms of y, which I'm going to, if I'm going to rotate around a vertical axis, I'm going to say y minus 2 equals negative cosine x, meaning, well, cosine x is equal to 2 minus y. And if I'm going to solve for x, I'm going to take inverse cosine on both sides. So x equals inverse cosine of 2 minus y. And so that's on the right. On the left, I have the y-axis, so that's x equals 0. And so I've got my radius now is going to be radius equals right minus left, but left is the y-axis, that's x equals 0, so it's going to be that. All right. Now my volume is going to be pi times the integral from y equals, okay, on this diagram I think it's a little easier to see because, okay, we said that was the line, I already told you that was the line y equals 2. This is y equals cosine x here, so that means that it starts at x equals 1, and then, you can kind of see by the symmetry, that's going to be y equals 2. So y runs from 1 to 2 here, so this is y equals 1 and y equals 2. And I've got pi r squared dy. And that's good. Okay, oh, and then we want to rotate e around the line x equals pi over 2. That's going to kind of give us, now there's something different. That kind of looks like a spinning top or something. Find the volume of the solid formed by rotating E around pi over 2. All right, so I'm going to draw a picture of E best I can and rotate that around x equals pi over 2, which is this vertical line right here. And so what we're going to need is, oh, I'm glad I put one of these on there because I haven't run into one of these yet with the problems I've been assigning. If I rotate around the y-axis here, I mean not the y-axis, but a vertical line like the y-axis, x equals pi over 2, that's going to require that I use two integrals, okay? Because right minus left is not consistent as y runs from 0 up to 2. So this is, you know, basically y is equal to 0 here and 2 there. And this is the line x equals pi over 2. Probably should write that in so we don't think that's a y-axis. This is going to be y equals 2 minus cosine x, but knowing that I'm going to be rotating on a vertical axis, I'm going to need x as a function of y, and so I'm going to copy that again. X equals inverse cosine of 2 minus y, and over here, x is just going to equal inverse cosine of y, which is not negative cosine. Because that's the curve y equals cosine x, so x equals arc cosine of y. All right, x equals inverse cosine of y. So now, yeah, from 0 up to 1, I'm going to have this as my radius. Okay, so I'm going to say radius 1 is equal to right minus left is pi over 2 minus arc cosine of y. And then we're going to go over here and have a second radius, and it'd be right minus left. Okay. And, well, I can write my volume. It's going to be the sum of two integrals. Pi times the integral from y equals 0 up to y equals 1 of pi times radius 1 squared. Wait, no, I already did the pi. Let's get that out of there. Pi times r1 squared. So pi over 2 minus inverse cosine y squared dy plus pi times the integral from 1 to 2 of pi over 2 minus inverse cosine of y squared dy. Just barely enough room to write that. And that's, if you really had to, you could use a calculator to find that. I will mention, for those of you that are interested, you could also use the shell method to find that volume, but that's not part of AP Calculus, so it's not going to be part of this video either. And that's all the problems for the 8.2 extra practice. You know, I'm pretty hungry. I think I need to go eat some lunch, and I think I'm going to record the online practice as a separate video, and so that'll probably be labeled like, you know, even more practice on discs or whatever. But thanks for watching.